So, if this is on, yes, great. So, welcome to another Microservices Meetup. This is the first meetup since 2019. So, there was quite a pandemic gap in there before we were rebooting this meetup. So, I'm so glad to see all of you again. So, this again, most of the people that are in the room right now, I believe I've seen in previous meetups. So who is here actually for the first time? Who has never been to a microservices meetup? That's amazing. It's about always, it's 1/3 of people who are here for the first time. Who has been here for more than 2 or 3 meetups? That's the rest. So, a lot. So I believe many of you, 2/3 I would say, have been here for multiple times, and I'm so happy to see you all again, and I'm welcoming those who are here for the first time. It was a great journey from 2014 to 2019, and hopefully from this year onwards we will continue this story. I'm very glad that David is with us today. He will do the presentation, he will introduce himself. And I'm also very happy and glad that he pushed me into doing the meetup again. He approached me and said, I've looked at the meetups in Munich, I'm from Vienna, I want to do something also, and I'm now in Munich, I want to be part of this community, and your meetup looks quite good. Let's reboot this. And he's doing the sponsoring, he organized the venue today, he's doing the talk, he's the co-organizer, so in essence, he's doing all of the heavy lifting. I'm just doing the introduction, I'm drinking beer, I'm eating pizza, and I'm talking with you. So I have the fun part, he has the work, he has to pay for it. Big applause for David, please. Yes, and I don't want to bore you with my babbling, how happy I am that we are restarting the meetup. And of course, watch the group for continuation. I will hand over to David. You will introduce yourself. We will talk about the sponsoring part a little bit. And then we'll hopefully, yes, a little bit. And then a very insightful presentation we are looking forward to.
Cool. Thanks, Christian. So yeah, I think you explained it very well. I kind of moved to Munich a few weeks ago, and then I talked to Christian and said, hey, I was very active in the Viennese community for software engineering and software architecture, and I saw this fantastic meetup with fantastic speakers in the past. What's going on? Why don't we reboot this? And this is why we are standing here now. So I think we also plan to do this more continuously now in the future again. And I'm very happy that I convinced the company I'm working for, Square, which is also now kind of has a small location in Munich, to take the sponsorship for everything, which is happening here today. As I said, we do this very usually in Vienna, so I'm very happy that we also start doing this in Munich. I will talk about the art of architecting for scale. So I work, I would say, my whole professional career in kind of distributed systems, whatever this means now in details, starting with microservices or service-oriented architecture. Usually I just call it service-based architectures. That's also the term I will use in the presentation. But who of you is working in distributed system right now? Guess most of you, otherwise you wouldn't be here, right? So it's nearly everyone. And who of you is working in a distributed system where it makes a difference if it goes down for a couple of minutes or hours, where this costs hundreds or millions of euros? Okay, also quite a few, that's good. And who of you will at least once during the presentation check the chat-ops channel on Slack if something is down right now? Okay, maybe me. Okay, one person. I feel you. So this is basically where I'm coming from, and I have the feeling, and I go a lot to conferences and meetups, that we talk a lot when it comes to organizations and scale about the optimization of flow, team topologies, how to structure teams, and so on and so forth. But I often have the feeling that we miss a little bit the technical foundation, which kind of, lays this whole thing so that we can build really scaling organizations and scaling engineering teams on top of this. And I think architecture plays a very important role, an essential one, and also chaos plays a very important one. So whenever you have any questions, feel free to interrupt me. Yeah, I think it makes a lot of sense here at meetups to kind of go into discussions. If you say, hey, what you are explaining here feels a little bit different in my organizations, feels a little bit different in the context I'm working in. So I, of course, work in specific contexts. So basically, probably where you are working on is something else, is where other solutions to given problems make sense. So first things first, as Christian already mentioned, my name is David. As you probably heard, I'm originally from Austria. I was grown up near to Vienna, and I live in Vienna since my studies, so to say. I was co-founder of a company called Square Solutions. So we started in Vienna as a very small kind of consulting company. I was before a lot in German, at German projects. And when I moved back to Austria, I had the feeling that there's something missing, which kind of makes sense to work for. And this is how I think most of the companies start, that you think you can make it better on your own. And we moved then to Munich beginning of this year and started here our branch to kind of grow our business also to Germany. So I'm anyway around after the meetup, so I think you don't need this contact information. If you have anything which you want to know, just feel free to reach out afterwards. So I would like to start the story a little bit with what's usually wrong in our industry, right? And we talked already up front a little bit. I work a lot with startups, so I worked a lot in my past with startups. I was also co-founder of a small startup, and now I work a lot with, startups that are, so to say, in the rise to scale-ups. And what you usually always see in our industry is the same thing, right? The more people you put into projects, the slower it usually seems to get, right? And this is very interesting when you talk to, founding engineers or founders of startups. They always say the same thing. I had the feeling that we were much faster when we were 10 people than we are now with 215. And maybe sometimes they're even right, yeah? The problem is not only that we kind of decrease our output in terms of delivery, but we also kind of increase heavily our issues in terms of availability and resilience in the broader context. Yeah? And this is where we usually end up in something which we tend to call a complex system, right? And we say this, I think, because it just sounds cooler, right? It feels cooler to say I work in a complex system instead of saying I work in a system where we didn't deliver a feature for the last 3 months, right? I work in a system which goes down every 2 weeks. But actually, it's totally against what we are striving for. And I like Dan North saying here quite a lot that we actually want to safely and sustainably reduce the lead time to thank you, right? Because I think that brings it very well to the point. We often say we want to reduce the lead time to production and so on and so forth. But in the end, it's the lead time to thank you, right? It's not just that we deploy something which nobody is using. It's really that we deploy something that is working sustainable, that brings value to our customers. And as I said before, the story usually starts with a very simple system, right? You, me, somebody as an engineer has an idea, knows how to solve a problem and starts with something, right? Starts with something small and figures out, okay, this brings value to somebody. Somebody maybe even pays for what I'm doing, right? Fantastic. And if you have in such a small, simple system a problem, then it's usually quite easy to find a root cause. You just go to the trace or to debug this stuff, and then you will quickly figure out what's going wrong, why is the system failing, and you can simply fix it, right? And everything is great again. And over time, as you build a great software solution for a given problem, your system will increase, right? You will put more things into your system. And from your simple system, you will come into a complicated system. And also, it's still a complicated system. The relation between cause and effect is usually given. So even in such a complicated system, something fails, you can usually, not easy, but somehow figure out where's the problem, and you will spot it at some point in time and will be able to fix it, right? And if your system continues to grow and grows and grows, you at some point in time will figure out this does not work anymore, right? You need to kind of start to modularize your system. And this is where we, take all these concepts which we learned for decades now, to introduce information hiding, to introduce the right abstractions, and to come up with modules how we split our system into smaller overseeable chunks. And I think this is exactly the point where a lot of things went wrong in the last 10 years in our industry, because modularization usually is a synonym for slicing this stuff up into smaller distributed systems. And that's kind of problematic, because I really sometimes have the feeling that when we talk about we need better modularization in our system, we directly talk about distributed systems. As I said, whatever this means, yeah, I don't want to go too much into the terminology war, but something which kind of runs on multiple workloads, which is kind of distributed. And that's a big misunderstanding, which I often discuss with our clients, that basically, if you think about it, you have two axes, right? You have on the one hand side modularization, and you have on the well and bad modularization, you have on the other hand side the amount of deployments units. So you can have kind of a monolithical deployment, or you can have a very distributed deployment. And where we usually are in many situations is somewhere on bad modularization and monolithic deployment unit. And this is what we tend to call a big ball of mud. And Joseph Joda, one of the authors of this paper, Big Ball of Mud, phrased it very well in his paper, that he said, sadly, architecture has been undervalued for so long that many engineers regard life as a big ball of mud as normal, right? And I think that's fully true. And this is where we started to kind of think, okay, big ball of mud is kind of a bad modularized system, so we kind of need to shift it into a more distributed system to become better modularized. And we all know where we end up, right? We usually end up in a distributed monolith, and we will talk about this in a second. And I especially don't like the term distributed monolith, because it kind of indicates that a monolith is something bad, right? A monolith is just a deployment unit. What we actually have is a distributed ball of mud, I would say. And when we just strive for modularization, then probably a better approach would be to go into this thing what we tend to call a well-structured monolith these days. So just what I want to say with this is that there are many good reasons, I think, to go for distributed systems, but modularization is usually none of them. Or as Simon Brown usually phrases it, you can't build a well-structured monolith. What makes you think microservices are the answer? And as I explained in the beginning that I worked my whole entire career in distributed systems, and now I tell you that distributed systems are not needed for modularization, it's of course interesting to figure out why do we need distributed systems, right? There's still a lot of use cases where we need distributed systems. I just want to kind of emphasize always that modularization is usually none of those driving factors. And if you think about the need for distribution, then you usually end up in two different branches, I would say. The first one is the pure technical reasoning. And there are usually three options why we go for distribution. And the first one is, of course, individual scaling demands. That we say, okay, this part of our application needs 10x scaling, and the other part just doesn't need to scale up at all, right? This is something which can be given, but in most systems I'm working with, that's usually not even the case, right? They have everywhere, so to say, a demand for scale, or they don't have a demand for scale at all. So this partial scaling, which I think was initially driven by companies like Netflix or Amazon when they introduced microservices to our industry, is in most business applications I'm working with, which are also heavily striving for microservices, not the main driver, right? Another reason could be technology segmentation. So we say we build all our microservices usually in Go, but we have this great machine learning Python library which we need to utilize, so we need to build one service in Python. Of course, makes sense. I think we've been over this line where we had this kind of flavor that we build each service in the technology of demands. And I think when we usually do it, it makes sense. And that's, of course, one of the reasons why you want to go for distribution. And last but not least is usually co-locating, right? That we say we want to shift our services closer to our customers. That, of course, also makes sense to carve out the segments and kind of be able to deploy them on a different location than where the rest is running, right? And these are, so to say, the technical reasons. Of course, there are a couple of more which we could discuss here. But in general, these are the pure technical reasons why you go for distributed systems. But as I said before, I think this is a minority in the cases where I see organizations going into distributed systems. And the main reason why, for example, our clients usually go into distribution is the concept of ownership, right? Is the idea that we kind of need to slice our huge system up into smaller chunks that independent teams can independently own it, and in the best case they can build it and they can own it, on the very best case they can build it and they can run it. And this is why in most situations we go for distributed systems, for example at Square with our clients. And then of course you could argue, but why do we need it here now, right? We said before that modularization is kind of a vehicle which you can use independently from your amount of deployment units. But if you think about it, and if you want to have those teams owning their service, being responsible for it, right? Also taking the consequences of the doing on those services, then of course it makes no sense to tell those teams that you own this module, you should fully be responsible for this module, you should run it, but you share your kind of deployments, or you share your platform with all the other modules which are implemented by other teams. So if I would be, for example, the owner for module C, I would never say I own module C entirely and I'm responsible that it's available, because I know that if module B, make something up which kind of will cause a failure, the chances are quite high that the failure will kind of make the whole kind of system faulty. And this is why we usually shift into distribution. We want to build services which can be independently owned by teams, which teams can feel responsible, because it's only fair to tell them you're responsible for this service because it's fully in your control, right? You kind of need to ensure that it's up and running. You need to ensure that we improve it. You need to ensure that it's resilient if other parts of the system are not working. So this ownership and responsibility is, from my perspective, the main driver why we go into distribution and why we should go into distribution. I think that's a very important aspect when it comes how we slice those services usually. And as I said, these are, from my perspective, the main reasons why we need distributed systems these days. And as I said, the majority of cases why we shift to distribution is actually the organizational autonomy and the importance to be able to scale engineering teams by giving them this autonomy which will get by this. And the idea is, of course, to kind of revert this graph and say, instead of kind of decreasing our flow, our output, our customer value, we kind of make it into smaller chunks, and those teams can kind of individually contribute in the sum then more to the given result. And this is where we usually then end in the autonomous service-based architecture where we want to end up in, right? That's the so to say the context for this talk, okay? And that's the easy part, I would say. The problem is when you shift from left to right, when you make, the transition on those axes from, a monolithic deployment to a distributed deployment units, then you usually also shift from a complicated monolithic system to a complex distributed system. And what do I mean by this? If you think of a single example, which I showed before, that I, as I said, worked a lot in banks. I usually still work a lot in banks and insurance organizations or fintechs in this area. And let's assume we have a lending system, right, where you can get a loan or will not get a loan. So the system decides, does this person get a loan or does this person not get a loan? If there's an error, if you don't get a loan for whatever reason, then it's usually easy to figure out what's the problem. You can just go again through the trace logs or debugger starter system and figure out, okay, there's obviously an issue in the age calculation, right? Which leads then ultimately to the effect that this person which should get a loan doesn't get a loan, and you can probably quite easily fix it if you work in this complicated monolithic system. If you now shift this system to a distributed system, and of course that's all very simplified, but just to make the point, if your loan calculation is not working again, then you usually end up in the problem that you're end of the analysis is usually here, because you figure out, okay, this service responds something which will on our side lead that the user is not allowed to get the loan, but the response is obviously wrong. And what you need to do then is that you need to go to the other team and say, hey, your response seems to be wrong, can you take a look at this? And this teams take a look at this and figures out, yeah, there's something going on here, and we figured out that basically the response we got from the other team is already wrong, right? And then they need to go to the other team and they need to fix it and so on and so forth. You get the point, right? So we are in a kind of complex system where cause and effects are usually not that related anymore. It's usually hard to figure out what is the cause of the effect, what is the cause of this issue, because our kind of analysis boundary is usually, kind of our team boundary in terms of this service which we own. So, in comparison to a complex or to a complicated monolithical system, a complex distributed system usually has a hard way. It's usually a hard way to figure out the relation between root cause and effect, right? Versus in a monolithical deployment unit, it's usually quite easy, so to say, hey, what happened? Where in this chain did things go wrong? That I can fix them, right? But there's a second thing which is heavily shifting when we shift, so to say, from the monolithical side to the distributed side. And this is where I usually in my workshops ask the people always to say, to figure out what is the difference between a method call within a single deployment unit. So let's say, we have module A, which is calling module B and which is creating a user, right? And a method call across the network, right? So basically the same business logic. You create a user, but instead of calling a method, you call a HTTP endpoint, which in the background then calls a controller, right? And I'll ask them, what is the difference between those two things? And the answer is actually very simple, everything, right? Basically, everything is different beside the fact that you want to create a user. And this is mainly driven by the problem that we usually don't have an issue anymore when we have this issue here, that we cannot create a user. Then the problem is usually not that there is a logical error in the system which we call, which says, I don't know, there's a bug which creates the wrong user and so on and so forth. Usually the issue which we get in distributed systems is a different one, is that the system for whatever reason is not available. Maybe we have network segmentation, maybe the system service is wrongly configured, maybe it just didn't start up at all, maybe there's a feature toggle disabled or enabled which should be disabled or enabled and so on and so forth. So we shift our problems mainly from reliability to availability. And this is also, I think, very, very good explained by the fallacies of distributed computing. Who knows the fallacies of distributed computing? Okay, quite a lot. So for those who don't know it, they were introduced by Peter Teutsch, I think in 1994, something like this. So quite old. So there are 8 fallacies. So things which you could believe but are actually not true in a distributed system, so that the network is reliable, that the latency is 0, and so on and so forth. So you can read them up afterwards. And the interesting thing is that the fundamental constraints of our networks didn't really change since 1994, I think. So these fallacies of distributed computing have mainly stayed true, have mainly remained the same as they were back then. And this leads us to the fact that besides the difficulty in figuring out the relation between cause and effect, we also have this different cause of failure, which usually in our industry was reliability. So something did not work, it returned the wrong result. So 2 + 2 was 5 instead of 4, right? That's reliable. A system is reliable if it creates, reliable results. And we invested a lot in improving this issue. We did testing, we did, lots of things. You can build up huge test bases to kind of get this problem of reliability somehow solved, right? I mean, solved. But you can, we have techniques, we have tools to kind of deal with this problem. The problem in complex distributed systems is, of course, we still have reliability issues, they don't go away, but we have a much bigger factor or vector of issues, which are usually availability issues, right? Which we did not have before, that a system is not available, that something cannot be reached, that something is only partially available, that only 20% of the requests go through, yeah? That some consuming system, some downstream system is wrongly configured and creates a lot of requests which the upstream system cannot deal with, and so on and so forth. So this initial idea that shifting, from monolithic to distributed systems to increase the scale of our organization, to be able to deliver more value, to deliver more customer value with smaller teams, usually or very often ends up in the problem that those systems are getting very unavailable, right? Those systems have a lot of outages, and these outages then sometimes lead to the fact that the teams again cannot deliver any value anymore, because they always need to fix these, strange Slack messages which pop up that some parts of our system are cannot working. And this is mainly driven, from my understanding, from my observation, and I'm happy to discuss this afterwards, that we treat those complex distributed systems the same way as we treated complicated monolithic systems. And what I mean by this is usually quite easy observable in again, a simple example which we had before, that, this landing system doesn't work. And then this team figures out, okay, this system returns wrong results. And they figure out, okay, there's obviously a wrong response, as we've seen before. And what they then do is they run through the whole organization to ultimately figure out, where is the issue. It takes them weeks to finally figure out, oh, the issue is here, right? And they shout at this team, the accounting team, and say, hey, can you please fix your stuff because our system is broken, because you return here some wrong results, right? And of course, at some point in time, we will maybe move it to the backlog and they will maybe fix it and so on and so forth. But this is a never-ending story, because ultimately there will be a bug, right? Ultimately there will be a database which will not be available. Ultimately there will be a network issue that those services cannot communicate with each other. Ultimately there will be a wrong configured service. So what we are still striving for in complex distributed system is a stable production. And I think this is fully elusive, that we can achieve a stable production in a complex environment and sometimes even chaotic environment. And I think the sooner we accept this, the better we are, right? And I think this is why we need to start to architect with failure in mind, as we, I guess, all know, that we say, another example, I work since a few months now with an e-commerce team which is building an online shopping experience or an online shopping system, where one of those teams then usually comes to me. In this situation, I picked up the payment team. Hopefully they don't see this now. No, they are fine with this. The payment team which comes to me and says, you know what, David, we are fully pissed. Our payment service is not working because the account service, did something wrong again, so our payment service is not working, we cannot execute payments, you cannot go to the online shop and buy something because payments are not working, and it's not our fault because the account service, has some issue, and the account service cannot return us the users, so we cannot do a payment, which is of course a problem for a shopping system, because, if you cannot buy something, you will probably go somewhere else, which again, lacks the whole idea of building a shopping system. And then I usually just ask him, but is it really like this? Is it really not your fault if you're responsible for the payment service, right? And if the payment doesn't work, then you need to figure out how to make it more resilient, how to make it better, that it's still working, even if one of the systems which you cannot control around you is not working. And of course, I guess also, again, everybody knows we should basically then ensure at least that not the whole payment service goes down if it cannot fetch users, but at least, return some reasonable answer to the user and says, hey, I'm sorry, we can currently not sell you something because, I don't know, we have internal issues and so on and so forth. Again, something you don't want to have in a shopping system because, as I said, payment flow is probably the most important flow which should more or less always run. So maybe let's think about introducing a cache or something like this, that we don't need the user all the time, and if the account service goes down every 2 days, 4 or 5 minutes, we can at least utilize the cache to figure out which users are available in our system. Or even better, we introduce some kind of, event-driven reactive systems where we have some Kafka topic where we kind of get all the user changed events, and every time a user changes, we source those into our projection and basically keep all the users in the way how we need them, right? And if the account service goes down, we don't care at all, right? Because we have all the users on our side and we can still execute the payment. Just as a very simplified example, right? And again, also on the other hand, we of course need to make our system resilient. If we have downstream services which we as a team cannot control, we need to take care that they will not be able to harm us. Because at some point in time they will have a wrongly configured service. They will have a bug which triggers 100x requests in comparison to the day before after deployment. And then we need to ensure that we have circuit breakers and load balancers and maybe also caching and stuff like this in place, right? Again, very simplified examples. We could go a lot in detail, but what I just want to say is that when we build, or when we want to architect for scale, we need to architect with failure and scale in mind. Because that's why we build these distributed systems in general. The teams can autonomously deliver kind of value. And if we then end up in a situation where we cannot deliver any customer value because we always say this service is down and this service is down and this service is also down, that's why we didn't work at all, then I think it doesn't really bring us forward in scaling our engineering. And the most important sentence, which I usually then tell to the teams, because of course it's more effort to build services in a very resilient way. But the cool thing is that a service that can run in a chaotic environment can basically run everywhere, right? But a service that can only run in a stable environment can unfortunately only run there and will break the first time when you have chaos. And you will have chaos, right? But we will come to this later. And the next thing, what we often then observe is that, for example, again, the payment team comes and says, yeah, this is nice now with the users, we don't have this problem anymore, but once we start to execute the payments, we are again reliable on a payment gateway team, and if this is failing, we cannot execute the payments, right? And this is usually where I say, wait, what? Why is there a payment gateway team? When you are responsible for payment, why is there an additional team which just takes care of interacting with all the payment gateways which are introduced? And of course, I fully get the point. I fully get the point that I don't usually say, but shouldn't it not be better in a kind of end-to-end verticalized way that you own the full customer journey, the full value stream of doing payments? And if you would do this, probably they would say, yeah, this is too much load. This is too much cognitive load for us. And that's a fully reasonable argument to say, introducing kind of interacting with all these different payment gateways in a thing on its own and, executing the whole payment flow is a thing on its own. But a more reasonable approach when we need to slice teams is, in my opinion, still to slice them very end-to-end vertical. And maybe a better solution, or where we ended up here, is to say, there's a SEPA payment team, which takes care of SEPA payments, and there's a credit card payment team, which takes care of credit card payments. Because when we do it like this, we slice up our system in two complicated end-to-end flows. Instead of, kind of slicing it up in a kind of complex end-to-end flow, which needs the interaction between two teams to kind of, fulfill the whole end-to-end flow. And that's a very interesting exercise, which I usually do when I go in architectural reviews, that I want to understand the main, kind of customer journeys, which are important for an organization, and I want to understand how many teams are involved. And if you count those teams, then it's usually a quite good indicator. Of course, not the only one, but it's usually a quite good first indication that you figure out how good are those microservices or these distributed systems sliced. So I think we usually want to architect for these end-to-end customer journeys. I think this should be our driving factor, that we ensure that we kind of build services which teams can fully end-to-end own, and with these end-to-end verticals they can also deliver then full customer value on their own. But again, all simplified here. There should always be a big disclaimer on each slide, very simplified, yeah, that's for sure. And I fully understand that we sometimes have situations where this is just not working. Let's assume that the context of fraud check, where there's some complex mechanisms going on to figure out, is this payment currently a fraud payment, or is this an allowed payment? And this is where we usually introduce this core teams, or in team topologies we call them usually complex subsystem teams, where a team takes care of something, which is kind of too complex for the cognitive load of one of those customer journey stream-aligned teams. And I think these 4 teams which were introduced here by team topologies, I don't want to go too much into detail, but we hear them a lot these days. I think they make a lot of sense. They're great terminology. I think it brings us a step further to have common understanding what we're talking about. But in reality, a team is always the same, right? A team needs to provide somehow customer value. And in a SEPA payment team, the customer is very clear. It's the person who wants to pay, right? It's the customer of this company. And we kind of optimize everything that this person, has a good journey, has a good feeling when it's utilizing our system. And for a core team, which is kind of, taking away a complex subsystem from us as engineering teams, the customer is also very clear, actually, if you think about this. The customer is just shifting a little bit into the organization to our engineering teams. And the same way as a customer, a real customer, would expect some quality criteria from our system, because if he wouldn't get them, he would just move to another system. We, as kind of stream-aligned teams, can expect the same thing. And when we introduce these core teams, I think it's very important that we talk about things like availability, that we talk within an organization to understand, hey, what is actually the availability of this fraud detection or this fraud checking service? What can I expect from you? What is the SLR, more or less? What do you provide me? What do you tell me that this service is available? Because, of course, this makes a lot of difference in how we architect our things. If we know that, this fraud check system has 3 nines, so is unavailable 9 hours a year, then we would probably change our system or our architecture heavily. We would, for example, introduce, I missed some parts here. Okay. Then this has an effect, of course, yeah. And I just added this note because I often hear then teams saying, most of the teams unfortunately don't have these metrics at all. They don't know the availability of the system. So usually quite bad if you work then, with multiple teams, and kind of teams are reliant on such a complex subsystem, and the complex subsystem cannot tell you, we go down every 2 weeks, or we are usually 5 9 available over the year. And of course, sometimes they tell us then, we have 4 nines, but we have every week a 2 hours downtime where we need to kind of update our system. So I think it's also important to mention that planned outages are still outages, and you need to architect for them, right? And in my workshops, I often then also ask the people, hey, can a service which has 4 9 availability, can a service have 4 9 availability if our dependencies have 3 9 availability? What do you think? Who thinks that this is possible? And who thinks this is not possible? Okay, half-half. It's usually always half-half. Of course it's possible. That's why we do all this thing, right? That's why we build distributed systems. They exactly do this to say, if you provide me a 3 9 availability, which says that you will go down 9 hours a year, then we need to architect for this. Then we need to say, okay, probably at some point in time, I will not be able to check if a payment is allowed. So I need to introduce some kind of rescheduler where we just say, okay, to customer, hey, we started your payment. It currently just takes a little bit longer. Sorry for that. But at some point in time, it will be rescheduled. At some point in time, it will be checked if it's allowed payment or if it's not allowed payment, and it will be executed, right? But if we, for example, say, okay, this system has a 5 9 availability, means it's down for 5 minutes a year, right? Then we probably don't need this. It's just an overkill. For 5 minutes a year, we can just say, hey, sorry, payment didn't work. Please click retry, right? Or retry on our own, whatever it is. So I think this kind of understanding of which availability our dependencies have is kind of crucial when we want to build these, scalable architectural organizations. And On the other hand, as I said, I not just only expect availability, I also expect, hey, what is your mean time to failure? What are other criteria which you as a customer would also like to understand from your system? Yeah, I mean, you usually don't do it that formal, but if you go to, I don't know, one of the websites you're usually using and it goes suddenly down every 3 days, you want to know it because probably you would kind of look for another website which provides you this value. And that's the same with these core teams. And from my perspective, that's also the same with platform teams. I don't want to go into detail about platform teams, but we do a lot in platform engineering these days. And for me, it's the same thing, right? It's only a shift of the customer, versus the customer in a usual team is the real customer, so to say. The customer platform team is, the development team. And that's why I'm so strong against, just to make a spoiler, that, you have to use the platform which the company provides you. Because if the platform is so shitty that the people don't want to use them, then they shouldn't use them, right? And the platform team should take care of that it's getting better, that people want to use it, right? And that's, I think, the whole idea of all those cross-laying teams. So we think we should really start to more focus on availability when we architect things. We need to understand what is this availability of our dependency. And availability is here a broad term, but we need to understand how much can we rely on this, how much resilience mechanisms do we need to introduce, how much do we need to change our business flow and our business logic by knowing that this system will be heavily down once we need it, right? And then, of course, in most organizations, we have this concept of complicated subsystems, but not in the sense of team topologies, but, kind of complicated and legacy, and nobody really takes care of it, right? And this is usually where you're in a sad situation, because if you have this fraud check service and nobody takes care of it, you will not rely on it, right? Because, if it goes down, if it, blows up, then it's your problem, right? And by the way, that's quite a good way to modernize architectures from my perspective, this inverse-converse maneuver to say, hey, here's the legacy system, we slice the teams in a way, we say, hey, you are responsible in this case for payment, so you will, as a team, when you're mature enough, will figure out, okay, if I'm responsible, if I'm kind of reliable that payment works, then I anyway need to start to carve out things from the legacy system into my scope so that I can really take ownership of those things, right? And that's usually what's happening then, that we kind of, carve out the data and the logic of such a legacy system in our system, right? And of course, the logic is usually the easy part, the hard part is usually data. But in this case, if we need the user fraud data, we of course also need the user fraud data on our side. And then we have a lot of readers and writers on those logical endpoints on the legacy system. And in most cases, to be very honest, right, we also have readers and writers directly to the database, right? And what we then usually do is strangle fig. We build an API on top of this new or old system. And at some point in time, we shift over the data. And then we need to shift over all the consumers and producers or readers and writers. And we will have a short downtime because we kind of, need to copy over the data and need to ensure that this data is not changing in the meantime and so on and so forth. And then probably our API is broken and we need to revert all these things, right? And this is where I personally get a heart attack, right? This is where I just don't get it anymore. And that's really a very sad thing. And of course, it's again over-accelerated, but that's how you usually see it, how it's working, right? And I think we totally miss here the mindset of kind of zero downtime migrations, where we say, we do it the simple way. We kind of let the data flow from right to left. Yeah, the simple way again. Yeah, every time I say simple, it's actually not simple, but it's simple as before. And we use some kind of change data capture, whatever mechanism we need, that we are able to kind of, whenever user fraud data changes or when user fraud data is updated or created, also have it on our side. And then we can already kind of, easily migrate readers and say, okay, this reader is now reading already from the new service because we can always ensure that the data is available. But usually the readers are not the problem, right? The readers are not why you migrate to new services, because the readers you can usually, kind of solve with database replication, and so on and so forth. The problems are usually writers, and the problem if you do this is that you need to first migrate all the readers before you can start to migrate a single writer. And that's why you usually also want to do this in the other direction, right? That's why you want to ensure that whenever somebody writes into the new system, kind of an event is triggered or whatever it is then in the technical background, that ensures that this data is also flowing back to the legacy system. And by doing so, you can kind of migrate writers and readers, which are usually owned by one team, which makes it from an organization perspective much easier. Because you can say, hey, we have now this API, you can shift your writes and reads to this new API, but you don't need to go to 50 teams and say, hey, you just need to migrate your reads now, that the others can start to migrate your writes, right? So this usually makes things from an organization perspective a lot easier, and this usually also kind of, harms this kind of fear from migrations, because if this writer is misconfigured, doesn't work correctly now with the new API, we can just shift it back, right? I don't know, we kind of even can work with a feature toggle and say, hey, go to this or go to that, right? And if it's not working, we shift it back, go over the weekend, or go into the weekend, fix it on Monday, try it again, and at some point it will work, right? And this is, I think, what we need to embrace, and this is just in the context of migrations, but we really need to embrace this zero downtime mindset in general, so that we need to always architect in a way to say, hey, we work in a distributed system. We can never ensure that we have usually those downtimes, because it can always be reverted, right? Even if we say, now everybody's changing to this new API at once, 2 days later, somebody can say, oh, we have a critical bug, we need to roll back. And then basically everything is kind of going west, right? And last but not least, to kind of get that back to beer and pizza again, I think we also need to kind of start to dance with the beast when we talk about architecting for scale. And what I mean by this is what I said already beginning, right? Actually, you don't want your production to run smooth, right? You sometimes want to run it as chaotic as possible so that as many things can go wrong and will happen when somebody is basically there, right? I feel much better to kind of, have an issue in production at 2 o'clock in the afternoon where the whole team is available than you having a production issue at 3 a.m. in the morning where some crooky developer needs to get up and needs to check, oh, what's going on? I have no clue, I want to sleep, right? So that when this actually happens, that you have the right answers, right? So I think we really need to start to embrace this chaos. So we need to make our production less run smooth on purpose. So we need to play around and say, okay, we introduce something like, for example, game days, or kind of concept of chaos engineering. Where I say, we shut down all this database because we are funny, and we do it now because we anyway know at some point in time this Postgres or MySQL database, or I don't know what people are using all the time, this MySQL database will go down, right? And we know it will happen, right? The question is just, are we prepared then? And do we do it the first time then at 3 o'clock in the morning, or do we do it at first time on a Tuesday at 2 p.m. where everybody kind of, has a fresh head to think about how we can overcome these issues and to understand what are the implications of our system, right? And I heavily do this, right? I'm a strong, I'm religious about this, I would even say, right? I don't care about who has a disaster recovery plan of his system. Who knows where it's currently living? Somewhere in Confluence, right? Which was updated 2 years ago, right? And who would really trust it, right? Who would say, okay, if our system has a disaster now, with our disaster recovery plan, we can do it, right? That's usually not the case, and you will have a disaster in scaled organizations. And that's why I'm such a meaning about, playing around with the network. Just introducing some firewall rules for 2 hours plan and say, this network connection will not work. How does our whole system react, right? Kind of playing around with some services, misconfigured services and so on and so forth. And I think that's so crucial for scaling architecture that we kind of need to embrace this chaos. Because as I showed on one of the previous slides, it's totally elusive then when we build distributed systems that we will not end up in a complex or sometimes even chaotic system, right? So let's quickly sum up what I showed you. So I started with this very important disclaimer for those of you who are maybe new to this kind of world of very distributed systems, and where more and more organizations go into this, of course, still a few years. But I think modularization is no good reason to go for distributed systems, right? Because when you go from monolithical systems to distributed systems, you shift from complicated monolithical system to complex distributed systems. And this needs total new tools. This needs a total new mindset to think about the systems. All the things we learned at universities and from our experience, how kind of, make monolithical system more stable, make them more reliable, is of course still important for our distributed systems. But it's unrealistic that we kind of will end up in the same situation, that we will end up in a situation where everything is always available because we optimized everything so great that we will never have an issue. We have issues, we will have a lot of issues, and we need to start to deal with them. And that's why I think these 5 points which I showed you today are crucial to architect around failure and scaling minds, to architect around end-to-end customer journeys, to let your architecture drive by the known constraints in terms of availability, to architect for zero downtime mindset, and last but not least, to embrace the chaos. Because only if you do this, I strongly believe, you will hopefully at some point in time end up in a target picture, which we all have in mind, to keep the flow of value high and the amount of outages low. Or as Dan Noah says, keep the lead time to thank you low, even at scale. I hope this was useful. Thanks a lot.
And so I hope there are questions. Yes, I already see raised hands.
Yes. First of all, thank you very much. It was a very entertaining and informative talk. So thanks for that. So a quick deep dive question. When you're saying about like this legacy system that you take over, and the readers are quite easy, but the writers, I've got a really bad feeling when I see the slides with the events. So typically the writers are like some old COBOL system where you just hand over some data somewhere. How do you do that with events? So typically you do like a straggler thick pattern or something like that where you mock the API and so on. Or was it just shorted?
So from getting data out of the system, so that the upper area, so to say,
so
we
readers
really
are easy.
Yeah, we usually really often use the tool from our toolback CDC, for example. But to get changes back into legacy system, right? That's what you're asking for?
Yeah, because you have got an error there with events, but
exactly,
I don't see how that works. For example, if it's a database from 1994 or so.
Yeah, sure. I mean, you kind of need to get the data into the legacy system, and I mean, depends then fully on the technology, but usually you can kind of introduce some endpoints which are just there to kind of write back data from new systems into the old system, so that the old system kind of has all the data, and that you can have readers and writers in parallel. The issue you usually have, and that's why this is of course very simplified, is eventual consistency, right? If you have now writers on two different sides, then you kind of need to ensure that your system still stays consistent, because you have latency in this kind of flow in both directions, right? Yeah, and this is where we usually then work with feature toggles, that this new API directly goes against the legacy system here, for example, right? And not directly writes into this database. And here we then have the full consistency, and we still let the data flow back. And once we know that all writers are shifted, we kind of set the feature toggle in another direction, that we update only here, and that this kind of gets just a read projection. Makes sense?
Perfectly.
Yeah. So this is, I would say, a talk on its own, this migration pattern. But of course, yeah, it depends really on the technical details. I just wanted to say that the zero... Yeah, okay, got it. Yeah, because usually we work here with events, because often you also have the issue that when you do this, we often shift into event-driven reactive systems, right? We want to migrate not just only to kind of, synchronous distributed systems, but we want to shift into something where you can consume events and say, okay, cool, I know what's happening in the system. And there you also have the problem usually that once not all readers kind of migrated from here over to here, do you actually see my mouse? Yeah. From here over to here, then these kind of, let's say it's a Pulsar or Kafka queue, is incomplete, right? Because it just contains a subset of all the writers which are just on a new system. And that's basically why we make this complete loop, that we have also the legacy writes in our new system, and then we have all the writes in our new system in an event queue, for example, where from day 0, everybody who is interested in events will find here a Kafka topic, for example, which has all the events, which is very powerful because usually you cannot start to use Kafka events, Kafka topics, because they're incomplete, and they are incomplete as long as not everybody is migrated, and this is, where you run in circles somehow. Sorry for the long answer, but let's maybe, if you have further questions, we can discuss them at the beer, yeah.
It's definitely an interesting area.
Yeah, first of all, thank you for a great talk. My question is more philosophical.
Okay, nice.
So you know that you need distributed systems from the get-go, but you don't have any historical data to what is the availability of the dependent systems. What do you do?
Yeah. I mean, I would first of all start to collect them, right? I don't need to say, I don't think we need so much historical data. It's really mean times to failure, for example, right? For me, always a crucial metric to understand the maturity of teams and organizations in general. People just don't know it. They don't know how often is the system failing, how long does it take to kind of fix the failure. So, I mean, if you don't have the data, you should first of all start to collect it, and then I think it just needs a few weeks to figure out, hey, what is basically the trustworthiness of the system, and how kind of, how much do you need to invest in resilience kind of tooling or mechanics to don't run into these issues then, yeah. But crucial that teams really know these things, right? Teams know them from the consuming APIs or the consuming dependencies, but also from dependencies which they have on the system, right? That they understand, hey, what can we actually give them in terms of availability? Yeah?
If I might augment, a good intermediate step is to actually talk about the objective of the other team. So what is your service level objective? Do you actually plan to be this number of lines available, or do you have less availability to actually planning for? So, because availability is something you measure afterwards, but what are you actually aiming for? Mm-hmm. is a good indicator if you don't have data.
Yeah, exactly.
I smiled when you said to augment, because I was thinking of asking for a microphone and say, to augment that, I wanted to say. Because I think the situation, correct me if I'm wrong, the situation is if you're building this client of the other service at the same time as you're building the other service, you cannot just wait for the data, because you were just saying that you need to architect understanding what the other service can do, no? Yeah. So I cannot wait until the other service is built completely, collect data. So one thing that I would recommend is assume that the other one fails more regularly, but don't do some drastic compensation setup there. For example, just say, sorry, I'm down now as well, or I cannot serve, or meaning going for simple solution first, and then observe, because you cannot survive on those simple solutions. If the other one doesn't catch up, then you need to re-architect and then adjust.
Exactly. I think that's a very good advice, yeah. Exactly. Not fully over-engineer once you don't know the kind of availability of the systems, but as you said, yeah, also fail fast, but then monitor this fail fast. And if they happen all the time, you need to invest more in compensation and other strategies, yeah. I think that brings it very well to the point, yeah.
I would come up, down again. Please raise your hands. You have more questions, certainly. Yes.
So maybe a question about, so do you know of any normative references for this type of, design decisions? Like, so I have a requirement that my system needs to be available with a specific rate. And there is a requirement based on, I don't know, some sort of safety critical requirements from a customer or from the entire system is safety critical. Is there some sort of like, normative reference for that kind of thing? Like a ISO, standard or some sort of framework which lets you maybe do that in a more systematic way? Because all of these proposals I've heard and what you said, it's super, I mean, it makes sense, right? But sometimes I need to prove that specific requirements, in specific areas, I need to prove that the system is available.
Yeah.
That so where do I go? What is the framework for that? Or is there a framework for that?
I don't know if there's some kind of ISO standard on how to kind of prove availability, but usually you kind of very transparently report it, right? Like you do on a published or public APIs, where you say, hey, this API was available the last month, that availability. I think we don't need to always over-engineer this within organizations, but I think it should go in a very similar direction, that somebody can take a look at Datadog or wherever you're storing your monitoring stuff then to figure out.
But even that, even how do you prove it based on data, right? You need to collect the data in a specific way. You need to, and that is kind of, in my experience, it's kind of under-specified. I mean, everybody's talking. Everybody knows that it needs to be done, but if you try to look for a systematic, framework, how to do that such that everyone understands what you do, and you simply tell them, look, this is what I did. It corresponds to the normative reference of that and that kind.
Yeah, but
that simply does not exist.
But that's the cool thing. You don't need to do this usually on your own anymore, this instrumentation, right? You get it for free with a service mesh, for example.
Exactly. I mean, you need to get creative and show it based on some sort of data, and you need to explain that every time, and it's very domain specific, and it differs from project to project, right? And why nobody kind of like, starts to develop that sort of framework? Or would that be an overkill? Because I believe we have collected enough knowledge to be able to do that, actually, right?
So to kind of come with I don't know, a few metrics up with the industry standard, I don't know them, I think there are some, right? There is a P99 and a P99.9 and so on and so forth, and there is kind of a failure rate.
No one knows that, and it is. I mean, you can... Exactly. Exactly. I mean, that would be a way how to approach it, right? Because probability is a science, and you can define.
Exactly. Yeah.
And probability is always based on observations. So you need to define how to collect the observations and how to store it and for how long, and these kind of things. But even if you go and ask the, sorry to say that, Amazon or Azure guys, okay, you claim you have this 99 or 4 nines availability of that specific service. Is there a proof? Can you prove it? Do you have how did you calculate it? They say, oh, well, we did it internally, and if you're interested, I can send you to the guy who did it, but okay, I mean, they do that. And that guy is super smart. I mean, he's super clever, and he knows, but that's not what I would expect that they give me a normative reference. Look, this is how we did it. This is the standard method to do it. Well, so it's just a food for thought. I mean, why don't we do that?
Yeah.
I believe we have people who have answers to that. Is this indirect? You're next.
Actually, it's just a 4 letters, ITIL. I'm pretty sure ITIL has a standard for that. And if you work with people who are fond of that.
Paul, I think it also depends on how serious you are to get this, because there are mathematical models. So, for example, if you go to a system that controls the trains in a city, you need to be able to prove what's going to happen. And there, I think the problem is that, so I spent quite some years into this domain, but the problem is that they become so complex if you look at typical software systems these days, that the question is it worth it? Or can't you not rely on collecting data? Because what you can do is you look at all your dependencies, calculate reliability of those, like how can they fail, what is your compensation model, so how do you want to react to it, what is the probability of that failing, and of course you can always build a model, still as a model, which they do for health systems, for transportation systems, but if you go to a service on Amazon or an e-commerce system, I don't know, it probably is not worth it, I think, at the end of the day.
Yeah, thank you first for the presentation. It's really useful. Yeah, maybe just one comment on that topic. Actually, there are for reliability, there is already some methods to calculate that using simulations. So I believe this is already solved problem. But what is really interesting for me, if we go to Amazon or if we go to Azure, you can look to their documentation and they have something called design patterns, for example. So these design patterns are really interesting. And my question to you, like you already mentioned, very interesting idea that a system that works in chaotic environment should work everywhere, but if stable, and then it doesn't work everywhere. So do you have a design patterns for the boundaries between the modules? Like imagine if I have specific, you already mentioned like caching and so do you have a suggestion for those boundaries so you can really systematically build that?
Yeah, I mean, there are a lot of patterns, and again, it would be in there. I have a few, I think there's a talk on YouTube where I go more into this, how to build and really resilience into service boundaries. And usually resilience comes a little bit with redundancy, right? Usually I do a lot of resilience with replication of logic or data. And I think this is where you gain your most resilience benefits by, as I said before, you can, of course, just simply do retries, or you start to cache, or you really, that's why we often shift so much into reactive systems these days, because everybody who needs users builds up its own projection of users, and so forth is not reliable anymore on this, central user system. And if this one goes down, everything goes down. So I think there's kind of, a journey where you then usually end up in mechanisms that you need to ensure that this data doesn't get stale, right? Because the more you project data into replications or read models, the more you end up in the issue that this user is maybe not, kind of valid anymore, because I don't know, somehow you didn't get the updates, or sometimes you run into eventual consistency issues. Yeah. So I think there is not the single answer to say, we build projections now for everything, and you kind of, you get all the data on your service which you need to run. So at runtime or at request time, you don't need any data anymore, which kind of means that you could basically serve every request if you really, kind of just theoretically think it to an end. But of course, this is not always the case. Yeah, and that's why I think, again, it's so important if you know the availability. And I know availability is just one term, but to understand a little bit the trustworthiness of the service. Because if you really have a user system, a legacy system, which goes down all the time, then you kind of probably need to CDC into a Kafka topic, for example, and build up your own projection of users so that you can still have the users when the request is hitting you. Yeah. That makes sense. There is, I think, a great, I hope that's not too much advertisement, but there's an Amazon sub-page kind of, which is called, I think, event-driven architecture patterns, which shows a lot of those patterns, which I just mentioned with projections. And of course, a lot of things which usually services measures bring you for resilience are good patterns and so on and so forth. Yeah. Make sense? Yeah.
Just one last question. Yes, so my last question is about the overarching services, or let's say the architecture of overarching services around the real architecture, like, for example, monitoring and the automation part of it. Like, how important is to consider them when we are building this modularity, for example? Like, do you consider, for example, monitoring before or after, or do you consider monitoring when you are building this modularity, or you just really think about the user journey or the 5 points that you mentioned?
Yeah. I mean, if you don't have tracing and proper monitoring and log collection in place, then I think that's the first thing to do before starting anything of the things which I said, right? Because it's so crucial, and you're fully right, you know, that's the Kano model. Sometimes I often forget to state or to seize the obvious, because really, if you don't have this, then you can skip all these 5 points and need to start with this first, right? And you're right, there are organizations which go into distributed systems which don't have a tracing system. I don't know, at least some simple Jaeger where you see where is, you know, the request failing within your distributed systems. And then sometimes it's the first way into distributed systems, and to slice the services then like database entities. And then you have 25 hops for a customer journey. You don't have a tracing, so you can just, you know, go home and start again.
One or two questions we would have time for, otherwise we will die out of. There you are. Just
sorry. Thank you. I really enjoyed the talk. I love your almost religious kind of mindset about chaos engineering. Maybe from your experience, share some words around how do you convince business to delete databases in production?
Yeah, that's usually easy after the first outage, right? Then it's easy to convince them. Yeah. Till there it's not so easy, and then you usually have this discussion. But can we really do it at 2 o'clock in the afternoon, or should we not do it at, I don't know, 4 o'clock in the morning? And it's fine for me if we do it at 4 o'clock in the morning, if they pay the whole team to be available there, right? And that's usually a cost question, yeah? But the point is, you know, once you did it, right, and once you then kind of can give the business also the certainty that you can deal with disasters, it's usually, I think, really, as you said, this first hop, that they see it once, and to see, hey, this brings real value. I mean, we do it because it brings value, right? We not do it because we are funny and we want to try out new things, right? Sometimes, yes, but in most situations, what engineers usually propose makes a lot of sense, right? And so it's the case there. Yeah. But as always, I mean, that's, I think, the role of an architect these days to kind of, you know, be good enough in argumentation and in convincement that, you know, he can kind of convince the business leaders or the managers to do things like that, right? But no clear answer on this, sorry for.
Thank you for your talk. Before you talked about when you're doing architecture reviews, you count the number of teams who are in between, who are on the critical path to do the business value. Where do you see limitations there? What do you think is the best number or good number of teams, or is this unlimited?
I think the best number would be 1, to be honest, right? To be very clear, yeah. And I think also Manuel Pace says this, that you should have really a small amount of this platform teams or complex subsystems teams, right? It should be 10 to 15% of your organizations, right? And if you take a look, and that's not blaming or ranting now, but if you take a look at usual enterprises and you take a look what these teams are doing, only a very small portion is really kind of, you know, delivering the concrete customer value. All the others are trying to kind of, you know, keep this complexity, keep this technical depth somehow in boundaries, right? And I think this is where the issue starts, yeah? So, of course, 1 is elusive in many situations, right? But it should be as low as possible, right? I mean, if it's 5 or 6 teams which are involved for the most critical customer journey through your system, then I think it's problematic. And maybe to just clarify this, if you involve, for example, a platform, so platform team for me, for example, doesn't count, right? Because it's not really involved, it just enables you, right? I think platforms But as I said, I think that's another topic. But platforms are mainly misunderstood these days, right? Like, they provide you something where you can run on. But the simplest platform, and I think also Manuel Pace says this, is basically a Confluence documentation which tells you how to spin up a microservice, right? That's also kind of a platform which a platform team can provide, and probably it's more valuable than the platforms we are building now at scale in many organizations, right? Fully against the customers, against the development teams, because not understanding what are really the pain points of the development teams. Why are they so slow, right? What would really benefit them, right? Probably not the fifth Kubernetes cluster, but probably something else which makes the life easier, right?
I would have a presentation for that one in queue. I had a lot of déjà vus during your presentation. I really enjoyed it. I was also curious about the directional flow, bidirectional flow of data. Yeah. That's typically the part where it's really getting interesting and you need a lot of context. I believe this is a topic to be discussed over beer and pizza and of course other topics. Thank you very much. This was a great presentation. Thank you very much for being here. Beer and pizza. Pizza is cold, beer is also cold, it's out there. Enjoy the rest of the evening and have a lot of good conversations. Thank you. Bye.